So this last video on the atmospheric environment is going to be on the ozone hole. This is a beautiful story of how science actually solved a problem. That doesn't happen all that often. And so with respect to the generation of ozone, as we discussed in the previous video, it occurs in the stratosphere. We have our ozone layer, and due to the prevailing winds within the stratosphere, a lot of the ozone is actually moved to the poles. So we actually have a higher concentration or amount of ozone at the poles than we do at the equator. But it's largely produced at the equator and then transported to the poles. And so we're going to talk about this formation of an ozone hole over Antarctica, which occurred in the 1980s. And so we've been measuring ozone in the stratosphere since the 1950s, and we started to see this decline in the 1970s. We didn't know why. And again, by the 1980s, we started to see a hole, a stratosphere void of any ozone. This figure shows the concentration of ozone in DUs, Dobson units, from 1980 into the 2000s. And we see this drop of ozone, and this is over Antarctica. This figure just shows the size of the ozone hole from 1980 to into the 2000s. And so what we saw was that the ozone hole was about the same size as the Antarctica continent at about mid 1980s. And this is what alarmed scientists and even politicians at the time. And it's continued to grow, and even to this day. Now it's about the same size as North America. And at this size and the way in which it meanders, this hole would sometimes even be over land, say in South America or even Australia. And so how did we solve this problem? So the first thing that we needed to do was we needed to find what was causing this hole. And so researchers, primarily centered at UC Irvine in California, they detected chlorine pollution in the upper stratosphere. And so their experiment, what they did was they used the moon as a light source. And they flew well up into the atmosphere, probably close to the stratosphere, on a jet or airplane with instrumentation. And they measured what wavelengths were being absorbed by the stratosphere. So their experimental design is pretty much the same as any spectrophotometer. You all have used a spectrophotometer where you have a light source and you know what that light is. So you know what we call the incident beam coming in to your sample is. And then you have a detector on the other side of the sample which can measure what wavelengths are being absorbed by the sample. If you know what's coming in, you know what's coming out, then you look at that data and you measure what was absorbed. And so when they did this experiment in the upper atmosphere, they found that the absorbance corresponded to chlorine compounds. And so this is where they looked in terms of determining how the ozone layer was being depleted. And so the chemistry over Antarctica is quite interesting. This is not a very straightforward chemical reaction. There's a lot involved. And so this is how the ozone layer, or ozone hole, is created. So in summer months, everything is normal. We get the production of ozone as discussed in a previous video. Now in the winter time, what happens over Antarctica, first off, is it is completely dark for quite a few months during the winter. No sunlight whatsoever. And of course, it's very cold. So within the stratosphere, we have these ice crystals, these ice particles. And what we're going to find is that these ice particles play a key role in the destruction of the ozone over Antarctica. So what is involved here is surface chemistry. We need that surface to bring different reactants together to create the destruction. And we also have photochemistry. In the end, what we'll find is light will play a role, as discussed in the previous video. It will play a role in the destruction of the ozone by the chlorine compounds. So let's continue setting this up in terms of creation of the ozone hole. So we have winter. We know it's dark for a few months and it's very cold. But also what occurs over Antarctica is the formation of this vortex during winter, which traps the cold air and also traps these ice particles, which form these polar stratospheric clouds, or PSCs. Now these PSCs, they come in two types. It depends upon how cold they are and also the pollutants that are present. But at around negative 80 degrees, we get these crystals to form, and they also, besides water, contain nitric acid. The other type, the PSC2s, which occur at slightly less cool conditions, they're mostly just water. But what's interesting about this situation is that this polar vortex traps whatever is in over our Antarctica at the time. And so it behaves like a closed system or a closed reactor. And so this is where the reactions will take place within this vortex. And so here's our vortex. And we have our polar stratospheric clouds containing different pollutants. And let's see what happens. So again, we have a lot of chlorine pollutants, things like HCl, other pollutants that react with the nitric acid on these particles. And on the surface of these ice crystals, we end up producing chlorine gas during the dark winter. And again, this is all just surface reactions with chlorine compounds and the nitric acid. And so what we get during the winter is a buildup of these chlorine gas molecules on the surface of these crystals. And then all at once, with the advent of spring and with solar radiation, all this chlorine gas that was produced over the winter in this closed reactor then produces a mass amount of chlorine radicals all at once. And it's these chlorine radicals that, as we know, destroyed the ozone layer, and they do so in such a quick and efficient way that it actually creates a hole over Antarctica. And so this is just a figure kind of showing the chlorine pollutants here and how they stick to the particles and concentrate at the surface and produce the chlorine gas, which then, in the presence of light during spring, creates all these chlorine radicals. And we see the relationship between the production of chlorine monoxide and the depletion of ozone. So as the concentration of chlorine monoxide goes up, ozone goes down. And so what occurred after this research is that politicians and world leaders quickly decided that we needed our ozone layer and that we would stop producing and consuming these chlorinated and brominated compounds. And so there was the Montreal Protocol, which began phasing out these halogenated compounds. And that's what we see here in this figure, where from the 80s on through to the 2000s, we see that we're using less and less of these compounds. And the one that is actually kind of growing a little bit is this hydrochlorofluorocarbons. Those are kind of the alternative to the CFCs. And the reason for that is by putting that one hydrogen on the CFC, that's what the hydro is, and we see that one hydrogen here, it really lowers the lifetime of the molecule. And so even if this molecule escapes into the atmosphere, say from the back of your refrigerator or at a mechanic shop as they're recharging your air conditioner, its lifetime is very short. And so it may just stay in the troposphere. And based upon its lifetime and residence time within the atmosphere, it will never make it to the stratosphere. These CFCs, they are inert. You could say they're Teflon gas. They will make it up to the stratosphere because their lifetime in the atmosphere is so long. We also have things like methyl bromide, which is used as a pesticide in strawberry fields. It is nice to see that it is also being phased out, because within the strawberry fields, what they do is they cover the fields with plastic, as you've probably seen, and underneath that plastic, they pump methyl bromide gas under the plastic, raise the plastic, and then that gas reacts with the soil to kill the nematodes and other pests. But nonetheless, it appears that they're also converting to some sort of other alternative. And so last, what we see here is we're really not out of the woods. We did eliminate the source of the problem, the chlorinated compounds, but we're still at levels where our ozone layer is not back to where it used to be. And so it looks like we're starting to bend. And so hopefully in a few decades, we can be back at you know, 1970s, 1960 levels in terms of stratospheric ozone in the southern hemisphere. So I hope you enjoyed this video, and I hope we generate some discussion in class about the atmosphere before we completely leave this topic.